Chapter 11, Stability. Conventional cosmology tests the stability of a universe by asking whether a self-gravitating fluid collapses under its own gravity. That question assumes 1. That matter is described by the local stress-energy tensor, 2. Space-time evolves via the Einstein field equations, and 3. Stability means resisting collapse or dispersion. Stability in this sense does not apply to the model proposed in this book. Instead, we work with a null geodesic effective geometry. The mass profile, m of r equals 2 pi kr squared, is an empirical construct derived from lensing, redshift, and horizon geometry. It does not arise from a fluid or dynamical stress tensor. Our focus is the geometry of null geodesics. From the previous chapters, the effective static spherically symmetric line element is this. A photon emitted at radius r and received at the origin experiences a gravitational redshift. The key properties are a monotonic redshift. The distance is 1-to-1 function of redshift. Null geodesic completeness. Photons from any radius reach the origin in finite coordinate time. No event horizon, no singularity. And C, finite curvature. All scalar curvature invariants remain infinite within the observed domain. Thus, the geometry is observationally complete and well behaved across all scales accessible to current cosmology. Perturb the surface density. The redshift at a fixed radius responds as this. So a 10% perturbation in K changes the redshift by at most 5% within the redshift domain probed by supernovae and baryon acoustic oscillations. The model is linearly stable to small changes in its fundamental density parameter. This response is damped further by a self-correcting mechanism. Variations in K shift the horizon radius, RH, which adjusts both the gravitational potential and the redshift path. These shifts act in opposing directions on the observed CMB temperature, resulting in a net cancellation. The temperature remains nearly invariant. Although the model is not a fluid, one can still ask what would happen if this mass profile were interpreted as a fluid. For Newtonian gravity, rho of r equals k divided by r, we have the pressure gradient is constant and negative. Pressure of r equals pressure at 0 minus 2 pi gk squared r, with no singularity or runaway instability. A relativistic check via the TOV equation shows us the same result holds when pressure is much less than the density, as it does on cosmic scales. The near-horizon Hawking-like temperature is around 1.4 times 10 to the negative 30 Kelvin. The evaporation rate is negligible, and the back reaction reduces this temperature as the energy escapes. This negative feedback stabilizes the horizon over cosmological timescales. We now formalize what observational stability means for scale-dependent geometry. For this profile, all criteria are satisfied. The profile is geodesically complete, curvature regular, and observationally robust. The conclusion is that the usual collapse test assumes fluid dynamics and fails to apply here. This model is a null geodesic framework, not a dust solution. Its observable predictions depend only on light propagation through a well-behaved spacetime. The profile is stable in every relevant sense, geodesically, thermodynamically, and hydrostatically. Critiques based on dust collapse or fluid instability are therefore misplaced. This is not a collapsing gas cloud. It is an effective cosmological geometry built from what we actually observe: redshift, distance, and the CMB. The model contains only a single free parameter, the Hubble constant. This parameter sets the horizon scale and thereby determines all other derived quantities, including the surface density, the Hawking-like temperature, and the gravitational blue shift needed to match the observed CMB temperature. Because these quantities are all interlinked, varying the Hubble constant changes the entire structure of the model. The horizon radius, the emitted temperature, and the required blue shift all adjust together. The observed CMB temperature is held fixed at temperature equals 2.725 Kelvin. So each variation in the Hubble constant implies a different emission radius near the horizon. The required value always hovers within a few Planck lengths, making the observed universe appear remarkably fine-tuned to support this thermal interpretation. Although some room for variation exists, the values of the Hubble constant that allow this internal consistency fall in a narrow band around 70 plus or minus 10 kilometers per second. This convergence of redshift temperature and curvature with a single tuning parameter is both predictive and falsifiable. Any claim that the model is unstable must explain why all parameters align so well. A collapsing or expanding version would require further fine-tuning to account for the Doppler effects, which would require adjusting the CMB temperature location of emission. While there is some room for adjustments, we can still conclude that Doppler effects do not account for a significant portion of the observed frequency due to the close alignment of the CMB temperature at 2 Planck lengths.